Hello, this is Mrs. Westmoreland, and here's a first review video, something that you should have learned pretty well in pre-AP chemistry for our discussion next time in AP chemistry. So we're talking about the mole concept. And to begin with, we're going to talk about relative atomic mass. So these are the masses that are the decimal numbers that we find on the periodic table. And you should know that those masses are weighted averages of all the naturally occurring isotopes of an element. We take a tool called a mass spectrometer, which allows scientists to measure the masses and the abundances, or how often they are found in nature. And the standard upon which relative atomic mass is based is 1/12 the mass of a carbon atom. And I'll speak to how that is used for the relative atomic mass in just a moment. So we use relative atomic mass when it's just single atoms. We use relative molecular mass when we're talking about the masses of molecules, so atoms that are covalently bonded to each other. We use the term relative formula mass when it's a cluster of elements of an ionic compound. So both molecular mass and formula mass are just the sum of the relative atomic masses of the elements in the chemical formula. But what units do you use? Well, the strange thing, and it's really derived from the fact that these are in fact relative mass, is that the same numbers can be used to calculate the mass of a single molecule or a mole of molecules. So when we're talking about the mass of a single molecule, we use the unit of AMU, or atomic mass unit. But a mole of molecules is actually measured in grams per mole. So what is this about relative masses? Well, here's an example that might help you understand it. So if we say a golf ball weighs 17 times more than a ping pong ball, then 10 golf balls would be 17 times heavier than 10 ping pong balls, and 1,000 golf balls would be 17 times heavier than 1,000 ping pong balls. And so the relative mass is the same as long as you have the same number of each thing. So the masses on the periodic table are relative masses. We know that one carbon atom weighs 12 times more than one hydrogen atom, and 10 carbon atoms weighs 12 times more than 10 hydrogen atoms, and 1,000 carbon atoms weighs 12 times more than 1,000 hydrogen atoms. So a mole of carbon atoms weighs 12 times more than a mole of hydrogen atoms. And so molar mass is the mass in grams of 1 mole of the element. And again, it's defined based on carbon-12, very common isotope. So 12 grams of carbon is known to contain Avogadro's number of atoms of carbon-12. So 1 mole of any substance contains that number of particles, and the molar mass of any substance is calculated using the same numbers from the periodic table, but this time using grams per mole as the unit instead of AMU. So mostly what that allows us to do is to convert between different ways of measuring matter. We can count the representative particles, we can measure mass, we can measure volume, and the method we use just depends on what kind of information we need. And then once a measurement has been made, we can convert between the units. So here are some of the relationships between moles and other measurements. Mole is equal to the molar mass, a mole is equal to Avogadro's number, and a mole of a gas measured at standard temperature and pressure is equal to 22.4 liters of volume. So the mole is the link between all those different measurements, and we can use dimensional analysis to make those conversions. So another thing we do with moles is we take experimental data and we find the empirical and molecular formulas of unknown compounds. So an empirical formula is a formula with the simplest whole number ratio of atoms, and it is determined by experiment. And the molecular formula is a compound in which the subscripts give the actual number of each element in the formula. So here's some examples. In some cases, molecular and empirical formula can be identical. In others, you scale up from the empirical formula to the molecular formula by some whole number factor. So chemists use empirical formula when they are able to analyze a compound for its percentage composition. They know what percentage of the compound by mass is each element. It can then find the empirical formula. And if the molar mass is known of the compound, then it can also be used to find the molecular formula as well. And so this is a very common practice experimentally to take some data and try to find both the empirical and the molecular formula of an unknown compound. So in the empirical formula, if you are given the percentages of each element, you can assume that it's 100 grams and convert the percents to mass. Then you change from mass to moles by dividing by the molar mass. Then you select the smallest answer of moles and divide through all by the smallest one. And then in that step, you will either have whole numbers or something very recognizable as a decimal form of a fraction. So it'll be 0.33 for a third or 0.25 for a fourth. And in that case, you'll need to multiply all the values by some number to make it into a whole number. Once you get whole numbers, then those are the subscripts that you write in the empirical formula. So here's the poem that is not really a poem, that represents those steps to find the empirical formula. You take the percent and change it into a mass. You take the mass and change it into moles. Then you divide by the small, then you multiply till whole. So molecular formulas are either the same as the experimentally determined empirical formula, or it's some whole number multiple of it. So in order to find the molecular formula, you must know two things, both the empirical formula and the molar mass. So first, calculate the mass of the empirical formula by adding up the masses from the periodic table of the elements with their subscripts in the empirical formula. Then divide the known molar mass by the mass of the empirical formula, and that should give you some whole number. That is the number that you multiply the subscripts by to get your molecular formula. So once you get sort of a sense of the importance of moles, the fact that moles are sort of the central unit in all of chemistry, you should be able to make connections between different units of measurement for a single substance, using moles as sort of the connection between all of those different units. And when you have a balanced chemical equation, of course, you can use the coefficients from the balanced chemical equation as your mole ratio to compare moles of one thing to moles of another thing. And we'll spend a lot of time practicing that kind of calculation. Another twist on your basic reaction stoichiometry is when you have a limiting and an excess reagent. So the limiting reagent is going to be the one that runs up first. It determines the amount of the products that form. It also determines how much of the other reagents are used. And the excess reagent is one in which there will be some left over after the reaction goes to completion. So if the two reactants are in a 1-to-1 mole ratio, you can just convert the given quantities of each reactant to moles. So whichever one you have a smaller number of moles of, that's the limiting reactant. And then you can use that limiting reactant to determine how much product can be formed and also how much of the other reactants are used. And also how much is left over. But that really has to be limited to when the mole ratio in the balanced chemical equation is 1 to 1. So whole numbers, one or no coefficients, just ones in front of your reactants. So if it's any other ratio other than 1 to 1, you're going to have to treat it a little more complicated to find out which one is the limiting reactant. You're going to have to factor in that mole ratio. So one way of doing that, I think the most student-friendly way of doing that, is to actually calculate twice using each of the reactants that you're given and choose the smaller answer as the true answer. And whichever one gave you the smaller answer would be the limiting reactant. Thanks for listening. See you in class.